case for our project as well. We are doing something very similar as well. So I'm not gonna go into detail on how the XNOPOP CNNs work from what they described. So what we are trying to do is do handwritten digit recognition using XNOPOP and convolutional neural networks. We are going to use the MNIST dataset. That's a widely used dataset for image processing that contains digits. So first, we are looking at binarizing the whole thing from the images, the filters, and through the whole neural network. So for the binarization, we'll be looking at different types of binarization and evaluating how that effect would be on the output result. So we'll be doing it in two phases, one using Python and one using VHDL. So first we'll train the models in Python and see what filters are best for the VHDL. So we are not going to do any training on VHDL itself, but only the implementation. After that, we'll do the same implementation on both Python and VHDL and see compare the differences and the performance. So first, we are trying to look at binary classification. Selahattin will talk more about that. Then we are trying to expand into multi-class classification depending on the time and the effort required. So this is the literature. So this is like an overview of what we are trying to do. We are trying to do one conversion layer and one fully connected layer first. We think it will give better results for binary classification from our initial findings. So as you can see, you have the input data on the leftmost side, and you have the filters. Here I've shown 3 filters with 3 by 3 grids. Those are all binary filters, and you feed that into the fully connected layer, which then outputs the results. So to talk about the data set, invite Selahattin.
Okay. As data set, we will use MNIST data set. This data set contains digits from 0 to 9. These are some examples. Some digits are easy to see, but like this one, it is not clear if it is 9 or 5. We have images like that, and each image has 28 by 28 pixels. We have 6,000 images for training, and for testing we have 10,000 images. Color values changes between 0 and 1. These values are floating point numbers, and we will be converting these values to binary. We will try these values to convert to binary. Also, first we want to see how will be this classification, if it will be easy or not. So we use a special technique for this. It is T-distributed stochastic neighbor embedding. It reduces dimensions to 2D, so we can see the classes images. So in here we have lots of images close to each other, so this part will be hard to classify. So we wanted to reduce the complexity. So we thought that we could do this binary. We can convert. We can categorize to these values. So we first assume that we can group round ones and not round ones. So we use the same technique, but we saw that it is not easy to using less convolution, less layers. So we thought that we should start with something simple. So at first we will try to classify zeros and ones. In our data set we have 5,000 zero values and 6,000 one values, and in the task set we have almost 1,000 zeros and 1,000 one values. So we will try to classify this one first, and if we have time, we will try to add more class to this problem. Okay.
Hi, my name is Niranda, and I will explain you about the VHDL implementation. As the previous group also mentioned, we will also be venturing into a very similar approach where we are using XNO operation and pop count for our implementation. So basically, when it comes to convolution neural networks, I'll reiterate this again. The convolution operation involves a lot of floating point operations. So using these in low power devices as well as on real-time operations could be problematic and would not be feasible and will be challenging. So that's where the whole idea of binary operation comes in, and that's where the XNO operation comes in. So we were evaluating whether to use XNO or AND instead of the multiplication operation in convolution. But looking at the literature and what the actual implementation of an XNO gate and an AND gate on hardware, it almost it's quite evident that using an XNO gate for the multiplication operation makes much more sense. The idea is using the XNO gate, it will give like an idea of the matching pixels between the filter and the image at each stride. So the convoluted, the XNO would give an idea of the multiplication, and the pop count would give an idea about the sum. So, but when it comes to the actual result of it, we would need to do a small scaling operation, which would still be an integer operation at the end for the whole convolution. That will be in the form of 2p minus n for the scaled result, where p means the pop count from the operation and n means the number of bits in the filter. This is just a small example to demonstrate how the scaling operation gives you the similar result to a binarized two binary vectors. It will give more or less the same result if we use that scaling operation at the end. So that is the first XNO pop would be used for the first convolution layer. Then comes to the all connected classification layer. We'll be using pop count as like a heuristic for the classification, followed by a threshold for binary classification initially, and then later on we would look at using different activation functions for if we are venturing into multi-class classification. And the pop count can be looked at as something like some pooling step in the middle, but we are yet to evaluate it. We would first evaluate these hypotheses on Python, and then once we have a more rigorous idea about the models, about the model, we would take it into VHDL. And we hope to complete it within 8 weeks. And we are at the moment working on the MNIST dataset as well as building a CNN model on Python, like a generic CNN model. And then looking at, we are planning to look at the XNOPOP model on Python. And then, as Sachith also mentioned, there binarizing the images would also would be a key part in this implementation. So we'll be venturing into that, and then the VHDL implementation. Thank you.
Thank you. So again, you need to break the whole project into several components, and each one can be in charge of one component. And in the final report, you can describe the problem you try to solve in this project, and what's the implementation, what's your implementation, and what's your testing scheme, so that you can prove that your implementation is wrong or right. Yeah, that's all.